We are now going to look very briefly at CMOS technology for constructing digital circuits. CMOS technology is using a type of transistor that is called a MOS, or sometimes also called a MOSFET transistor, which is short for metal oxide semiconductor field effect transistor. So while the MOSFET is the type of transistor, the CMOS is the actual technology that is used in order to create our circuits based on the MOS transistor. And this technology was patented in 1963, but the transistor was developed in 1959. And CMOS is just one of several ways to build digital circuits. There are other ways to design our gates, such as using, for example, what is known as resistor-transistor logic, or what is known as transistor-transistor logic. The CMOS technology has a few attractive properties that makes them very good for building digital circuits. First of all, they are very noise resistant. They are also very power efficient, so they have a very low static power consumption. And a third property that is very attractive is that they can fit into a very small area. There are two types of MOSFET transistors, and these two types are what are used in order to build our complementary design, that is CMOS. So let us first look at the type that is called a p-type. For the p-type transistor, we have the symbol shown here, and the input here is called the gate. Here we have the source, and here we have the drain. And the distinguishing feature of the p-type transistor is that this is here denoted by a small circle at the gate. We are not going to go into the physical characteristics of the transistor, but we will instead just try to understand how we can use it in order to realize a digital circuit in the CMOS technology. So a property that we have here is that the source of the transistor must always be connected either to the voltage supply that we have here in our picture, or to another p-type MOSFET transistor. And how this transistor operates is that when the input is low, so when the gate here represented as a G is low, it means that we have a low resistance between the source and the drain. So we will have this path here being conductive. But when the input is high, so when the input is a 1, so we have a 1 at the gate, it means that we have a high resistance between the source and the drain, so this can be seen as cutting off the connection between the source and the drain. So when we want to try to understand this resistor, we can model this as just a switch. So the switch here is closed when the gate is 0, and we have here the source and the drain, and the switch here is open when the gate is 1. So nothing can flow here between the source and the drain. But this is just how we model it. In reality, there will be some small leakage current here between the source and the drain, even if we have the gate equal to 1. But this leakage current is very small, and this is an attractive property for these types of transistors. The N-type MOSFET is the other type of transistor that we're going to look at. This N-type transistor is written typically in this way, and what we can notice here is that the difference between the N-type and the P-type is that we are lacking this ring that we had here for the P-type. We have the gate as being one of the inputs, and then here we have the drain, and this part is called the source. And physically, this is a bit different from the p-type transistors, since here the source must be connected either to the ground or to another n-type MOSFET transistor. And here we are not going to go into the details of why this is the case, we just are going to take it as a fact. And different from the p-type transistor, when the input, when the gate here is low, so when this is a 0, we have a high resistance between the source and the drain. And if the input, the gate, is high, then instead we have a low resistance between the source and the drain. So when the input here is a 1, then there is a connection here between the source and the drain, and when it is a 0, there is no such connection. And again, we can model this behavior as a switch. So when the gate is low, it means that this switch is open, and when the gate is high, this switch is closed. But again, this is just how we model it. There will be leakage current. So for our CMOS design or our complementary design, what we do is that we use both N-type and P-type transistors. So for each N-type transistor, we are going to complement this with a P-type transistor. And what we do is that we connect the input to the gate of both of our transistors. The idea of doing this is that only one of the transistors will now be open at a time. So we will never have a short circuit between the voltage and the ground, which means that we will have very low power consumption when the state is not switching. We can see this when we model our transistors as switches. So in this example here, we have a P-type transistor here, and we have an N-type transistor here. Now assume that the input to this is high, that is, we have a 1. If we now model this as a switch, the P-type transistor will be modeled as an open switch, and the N-type transistor will be modeled as a closed switch. So if we have the voltage supply here, and then we have the ground here, it means that we have now connected the output to ground, so output will be 0 when the input is a 1. And if this here really is an open switch, there is no current flowing from the VCC here and down towards the ground or to output. This means that we have a very low power consumption.